Hello everybody, so this is Christopher White, and in this video we're going to be doing exercise 11 from Interpreting Earth History by Ritter and Petersen. So you can actually find the exercise in question on page 155. It would have helped if I'd gotten my book ready, but I didn't, so here we are. Okay, so here's page 155, obviously title at the top, exercise 11. The learning objectives are here in the purple rectangle, and there's a few words down here at the bottom about the theory of plate tectonics. So we're going to skip past that. You can read that for yourself. The exercise itself begins on page 156. We're actually going to skip past part A, we're not going to do that, and we're going to go straight to part B. So part B focuses on the rate of spreading at a ridge in the mid-Atlantic. So what we're aiming to do is we're aiming to try and calculate exactly how far, or how fast should I say, new seafloor is created. What's the rate? So if we look at page 159, here is a stylized diagram of our spreading ridge. So you can see here's the Rift Valley in the center. Here's the actual point at which new crust is created, this dashed line here. And I'm sure you remember, because of course you've watched the presentation by now, you'll know that any crust that's created on this side will slowly be pushed laterally this way over time, and any crust that forms on this side will slowly be pushed this way laterally over time. So one of the ways that we know this lateral movement of the crust is occurring is by measuring the polarity of the seafloor. Now, once again, if you've watched the presentation, you will know that when we take a magnetometer and we pass it over the seafloor, we see there are changes in the polarity of the seafloor rocks. Sometimes the polarity of the seafloor rocks are normal, and sometimes the polarity is reversed. And of course, what normal and reverse means essentially is which way are the north and south poles orientated. So the black lines on this diagram here, take this one here, that represents periods of normal polarity. North is north, south is south. In contrast, the white areas, they represent periods of reversed polarity. South is north, north is south. So this polarity essentially is locked into the rocks in the iron minerals, and of course once the iron mineral drops below its Curie point, the polarity at that time is locked into the iron mineral, and so the rock retains that signature in the iron minerals. So okay, what are we going to do with this? Well, we're going to use these changes in polarity to help us work out the rate at which new crust is being created and old crust is therefore being pushed laterally away from the ridge. Alright, so let's start by going back to page 156. So the first question here essentially is asking you, let me get the page straight there, thank you. Okay, so essentially is asking you why the belts of polarity are the same either side of the spreading ridge. Well, once again, if you watch the presentation, you'll know the answer to that, so I'm not going to help you with that question. You can work that one out for yourself. On to question 2 though. So question 2 is asking you to calculate the rate at which spreading occurs at the ridge. So alright, how are we going to do that? Well, if you remember, a rate is essentially something like distance over time. So it's a measurement over a period of time. So what we need to do is we need to come up with a distance over time. So here's our situation. Here's our ridge. And what we're going to do is we are going to pick a point on that ridge. Now, points A and B have been picked out here. They've purely been picked out for a later question, so we don't really need to worry about A and B right now. We can pick anywhere. Now, the other thing that we have for this question is figure 11.4, which is this one down here. Okay. Now, what you'll notice is these purple bands here correspond to the black bands here. So, for instance, we have the Jaramillo here is J here. It would really help if I got the there you go, the diagram in shot. There we go. Is J there. The Olivi here is O here. So these correspond together. So in order to make our life easy, what we're going to try and do is we're going to try and find where one of these periods of normal polarity essentially hits a nice round number. So for instance, if we look here, this portion of the Gilbert right here, the end of it hits pretty much on 4.5 million years. This period of the Gilbert here, the end of it falls pretty much on 4.75 million years. So just to make your life easy, you know, it's just really helpful if you try and pick a period of normal polarity that falls essentially right on one of these marks. So if we look at the mammoth here, you can see the end of it falls nearly perfectly on 3 million years. Now remember, we are not looking for, you know, perfect numbers. So, you know, if it's hitting about 4.75 million years, just go with 4.75 million years. Don't overthink it. Okay, so this is how we're going to work out how long it takes. So what I'm going to do is I'm going to use this measurement here at the base of the Gilbert. All right, and as we just said, that corresponds to approximately 4.5 million years old. So it's taken this piece of crust 4.5 million years to go from the spreading ridge here to its present position here. All right, so that's a good piece of information. So next we need to know how far it's traveled. That's the other thing. So now we've had time, now we need to work out the distance. How far has that piece of crust actually gone? So what we're going to do is we're going to have to grab our ruler. There, voila. And the first thing we need to do is we actually need to measure the scale bar located here. So what we want to do is we want to work out what does 1 millimeter on this diagram represent in terms of distance. Now, please remember, we are doing this from a scientific point of view. That means we're going to be working in millimeters, centimeters, meters, kilometers. All right. I'm afraid imperial measurements are not useful during this particular exercise. So the first thing we're going to do is we are going to measure our scale bar. Okay, and our scale bar, which is corresponds to 100 kilometers, is 7.2 centimeters long. So that's essentially 72 millimeters. So what we're going to do is we're going to take the 100 and we are going to divide it by 72. And when we take that number, that's going to give us a number of somewhere around 1.4, 1.5. You'll do the calculation yourself to get the correct answer. And that means every 1 millimeter on this diagram corresponds to, let's say, 1.4 kilometers. All right, now that's very, very important to know because we're going to need that later. So what we're going to do next is we're going to measure the distance from the base of the Gilbert to our spreading ridge. And so we're going to take that measurement, and the measurement is going to be 5.7 centimeters, which is actually 57 millimeters. Okay, so our measurement is 5.7 millimeters. Now, what we're going to do in order to get our actual distance is we're going to take that 5.7 centimeters or 57 millimeters. We're going to need to use the 57. Okay, so we're going to do 57 millimeters multiplied by 1.4. Okay, and that's going to give us our distance. Now I'm obviously not going to tell you the answer. You guys are going to do this yourself, so I'm afraid you're just going to have to, you know, go with whatever you get. So anyway, sorry, I do apologize, I'm moving something around on my desk. So we've just done 57 and we've multiplied it by 1.4, and that's going to give us essentially the actual distance from there to there in kilometers. Okay, so once we have that answer, now please remember that answer is in kilometers. And if we just go back to the question for a second, what you'll notice is it asks for the rate in centimeters per year. So we need to take that kilometer number and we need to change it to centimeters. So if you remember, in order to change kilometers to centimeters, you obviously need to bear in mind that there are 1,000 meters in a kilometer and 100 centimeters in a meter. So please bear that in mind. So obviously whatever answer you get, multiply by 1,000, that's going to give you the number in meters, then multiply by 100, that's going to give you the number in centimeters. So it's going to be quite a large number. You're probably looking at a number somewhere in the millions. Excuse me, please. Okay, so that would be your distance in centimeters. So that's the first stage. Next, of course, you're going to need your age in millions of years, and you're going to need to turn that into years. So for argument's sake, let's say we have an age of 3.7 million years. So here's our age. So we're going to have an age of 3.7 million years. Now, in order to do the calculation, we've got to take this and we've actually got to write it out in the full sense. So it would actually be 3,700,000 years. Okay. So please bear that in mind. So when you do the calculation, you're going to be using a number like this. You're not going to be using 4.75 or whatever, value you have off this diagram here. So please remember that. So what we're doing now is we're taking the distance from here to here. We're taking the age of the rock of the Gilbert Formation here, which we've lifted off the diagram here. And if you remember, the distance has been converted into centimeters. We've converted the age into years. And once we have those two values, well, it's a relatively simple calculation. All we're doing is we're taking, it's going to be the distance divided by the years. Because, of course, the rate we're looking for is centimeters over years. So it's going to be distance divided by years. And that's going to give us the rate at which our plate is moving. Okay, so it's actually quite a straightforward exercise when you think about it. Sorry about this. I'm moving stuff around on my desk. I'm afraid I don't have much room to work with. Okay, so that was part 2. I hope that made sense. Next on to part 3. So part 3 deals with, well, asks you to put this rate of plate motion you just calculated into the blue box labelled B on diagram 11.2. So you'll find diagram 11.2 here on page 158. And so here we go. Here's our diagram, and box B is right there. There we go. Lost it for a second. And so you're going to put the rate of spreading you just calculated into this box right here. That's it. Nothing special. Just write the number in there. Done. Okay, so what's next? So next we're going to come on to question 4. So we are now going to estimate. Please note the word estimate. This does not have to be, once again, a perfect number. We're looking to kind of try and keep things simple. So try and keep to roundish numbers, thereby making your calculations a little bit more straightforward. So estimate the time necessary for the spread of the South Atlantic between Africa and South America. Okay, so what have we got here? So this is what we're dealing with here. So the first thing we need to know is what's the distance between this point and this point. Well, once again, we're lucky there's a nice scale bar down here for us to work with. And so what we're going to do first of all is I'm going to just quickly turn my answer book over here, which I've got hidden in the corner. Okay, so first of all, we're going to measure the size of this scale bar, and the scale bar here is about 2.9 millimeters. Now I'm going to measure the distance over here, and the distance is, will you look at that, 2.9 millimeters. So we've just gotten rather lucky. So that means the distance between here and here is 5,000 kilometers. So that's worked out rather well for us, hasn't it? So what we're going to do next is we're going to come back to our question. And so we now know the distance between South America and Africa is 5,000 kilometers. Now, once again, remember, we are not going to use that whole number because we are dealing with half of that number. Because if you think about it, once upon a time, Africa and South America were in direct contact with each other, essentially where the modern spreading ridge is now. And over time, South America has been pushed this way, and Africa has been pushed this way. So we're not worried about how long it took them to move the full 5,000 kilometers. We are only worried about how long it took them to move half of that number. So 2,500 kilometers. So don't get confused on that point, because if you go for 5,000, that's going to give you a rather large answer. Okay, so Number one, we're dealing with 2,500 kilometers. Now, once again, this is a number in kilometers, so we have to convert that to centimeters. Remember, 1,000 meters in a kilometer, 100 centimeters in a meter. So just do that calculation just like we did for question 2. So next all we're going to do is we're going to take that distance in centimeters, and we are then going to divide by the rate that we calculated for question 2. And when we do that, essentially we've got distance divided by distance, so that essentially is going to cancel them out, and all we're left with is how long it takes for the spreading to occur. And now remember, that number will be in years, so it might be quite large, so you may have to just simplify it a little bit by saying millions of years, just to make the number a little bit more helpful. But anyway, that's, once again, it's a relatively simple question. You'll actually see that this process is a very, very simple process in terms of calculating exactly how far these ridges are spreading. It's not actually that difficult. And then finally, we are down here onto part 5. Please excuse me. So part 5 is looking at points A and B on our spreading ridge diagram. So there's A, there's B. And so what are we going to do? Well, of course, the first thing we need to do is we need to get our distance. So here we go. So obviously we're going to measure A. A is going to be about, what, 5.1 millimeters, and B is going to be about 7.7 millimeters. Once again, take these measurements for yourself. Do not trust me. I could be lying. So once you've got those measurements, then of course do your conversion. Okay, remember, for every 1 millimeter on here, there's going to be something like 1.4 kilometers. Okay, so remember, make that conversion, and once you've converted it into a distance, okay, you've got that. Remember, once again, the distance is going to be in kilometers. You have to convert that distance to centimeters. So it's going to be, remember, number of meters in a kilometer, 1,000, number of centimeters in a meter, 100. All right, so anyway, once you've converted it to a distance, well, once again, you are then going to quite simply divide it by your rate of spreading. Okay, and once you've done that, once again, you've got distance on one side, rate of spreading is centimeters over years, so you've got distance, centimeters over years, so centimeters on one side, centimeters on the other side, they cancel each other out. What you're left with, once again, is years. And that's it. So it's not a particularly tricky question. You just got to measure the distance from A to B, convert it into kilometers, take that kilometer number, convert it into centimeters, and then divide by the rates you calculated for part 2. Done. Simple, no mess, no fuss. All right, so I hope you managed to get through that relatively quickly, relatively easily, and you find it relatively straightforward. But don't just do the calculation. Make sure you read the questions properly, do the steps, and you will actually begin to understand how we do it. Okay, that's how, so we begin to understand how geologists actually calculate these kind of rates. Okay, so once we've done this, we're going to move on to part C. Now, part C, as you can see here, consists of a table, which I'm going to try and get into the full field of view. There we go. And I don't want much for part C. What I'm looking for is simply a modern example of each of the different types of boundary in the white squares. Not the purple squares, ignore those. I'm looking for a modern example of each of these types of boundary. So a modern example of a continent-continent divergent boundary, a modern example of a continent-continent convergent boundary, and a modern example of a continent-continent transform boundary. Okay, you'll be able to find this information very, very easily, because in this particular instance, Google is your friend. So hit Google and you'll be able to get this table done in a matter of minutes. Okay, good. The reason we're doing this table is because we want you to have a look around and just try and find some modern examples. So when you find a modern example, all right, so let's say you find a modern example, it tells you something like the San Andreas Fault in California. Not going to tell you which one it is of these, but it would fit in for one of these boxes. So let's say you find the San Andreas Fault. Don't just write San Andreas Fault in. Take a second. Look at the images on Google. Maybe just jump on Google Earth. Have a look. Look at a satellite image. See if you can spot the San Andreas Fault. So it's one of these instances where the question itself is rather simple, but if you're just willing to spend just 2 more minutes just having a quick look around on the internet, you can find some absolutely wonderful information about these types of plate boundary, genuinely interesting stuff. So don't just fill out the table, just take a second if you can. All right, so next we have part D, and as you can see, part D has 2 pages of, well, pretty dense data, and that is why we are not doing part D, because let's face it, we have lives, we need to do stuff. We'd be there forever. So we're going to jump straight to part E. So what's going on in part E? Well, part E focuses once again on rates, but in this instance we are going to be using Hawaii as our focus. So here we go. If you look at page 166, you will see a table at the top, and you will see a simplified diagram of the Hawaiian Islands down here at the bottom. Okay. You will also see there are several locations marked out by white circles, and each of these white circles has a date. Once again, we also have a good old-fashioned scale bar there at the bottom. So what's the aim? Well, we're pretty much doing exactly what we did with the spreading ridge question in part B. So the first thing we're going to do is, number 1, draw a line. That's what it wants you to do. Read the question, do it. All right, not difficult, just get it done. Part 2, which would really help if I had it in the field of view. There we go, that's far more helpful. So using figure 11.6, 11.6 is the Hawaiian Island diagram here. Fill in the data pertaining to distance and age differences between the sample stations located on each island in table 11.3. So here we go. So we have our table at the top here, and we have our map down here at the bottom. Okay, so what it's asking us to do, first of all, it's asking us to measure the distance between 2 locations. So here are our locations, location 1 and location 2. Southeast Maui, Northwest Maui. Okay, so we're going to come down here. Well, there's the island we're looking for. Our first location is southeast, so it's clearly going to be this location here. And the next location is northwest, so it's clearly going to be this location here. So we're going to measure the distance from between these 2 points in millimeters, and we're going to convert that into we're going to use the scale bar down here to come up with a distance in kilometers. Now, once again, don't go over the top here. All right, just try and keep the numbers relatively easy. Don't go mad. Okay. Now, once you have your distance in kilometers, you're going to convert that into a distance in centimeters. Once again, 1,000 meters in a kilometer, 100 centimeters in a meter. Okay, so you'll know how to do that calculation by now. The next thing we're worried about is the difference in years. So what have we got going on here? So the northwest location is 1.3 million years old. The southeast location is 0.7 million years old. So I'm sure you guys can work out relatively quickly that the difference is 0.6 million years, or 600,000 years. So obviously you would be writing 600,000 years in here. And then the next thing you're going to do is you're going to calculate your rate, which is centimeters divided by years. So there's your number in centimeters, there's your number in years, and from that you can calculate your rate. Not difficult at all. Okay, and so you're going to do this for each of the locations. Okay, you're going to go from here to here, from here to here, from here to here. Oh, from there to there, from there to there, there to there, there to there, and there to there. And then the final one is it's going to ask you to do the largest one, which is going to be from here all the way up to here. And you're going to see that maybe the rates have stayed the same, or maybe the rates have varied. I'm not going to tell you the answer to that. You're going to see it in your numbers. Okay, so part 3. Has the rate of plate motion been constant? Well, that's a simple yes or no. Has it been constant? Yes. Has it varied? No. What is the range if there has been a variation? If there hasn't been a variation, then obviously the range is going to be 0. Finally, part 4. Enter the average rate of motion into the blue box labelled A on 11.2. So once again, we're going to go all the way back to page, where are we? To page 158, and we're going to enter our average rate of motion here in box A. Okay, we're doing pretty well so far. We're working our way through this lab very, very quickly. We're feeling pretty confident, aren't we? All right, so we've done E. We managed to work our way through that. The final lab we're going to look at is part F. And part F focuses on the Aleutian Trench. The Aleutian Trench is, of course, located in front of the Aleutian Islands, or should I say to the south of the Aleutian Islands. And once again, I'm sure you guys know, but the Aleutian Islands is a chain of volcanic islands that stretches here from Alaska all the way over to Russia over here. Okay, and as you can see in front of them, this green line is denoting where the trench is located. As you can see, you've got an arrow coming this way, arrow coming this way, so it's a convergent plate boundary. Okay, so number 1. We have table of data 11.4 here. I've really got to stop putting this at an angle. I do apologise for that. So we have a table of data 11.4, and down here at the bottom we have another diagram right here, which is diagram 11.8. And so what we're going to do is we're going to plot the data from table 11.4 onto diagram 11.8. So for instance, our first piece of data is going to be distance -5, depth 15. All right, so I'm going to put this up here. I'm going to try and get it straight. Now, please bear in mind, as you can see, that's 0, that's -100. So these are pretty broad squares. That's 50 essentially. So it's quite fine data like -5 is going to be a little bit difficult to plot, but we'll do our best. So the distance was -5, so it's going to be falling probably somewhere in around here, and the depth was going to be about 15. So actually, it's probably going to be pretty much where I had my pencil, so I'm just going to make a mark there. Don't have to label it 1, just going to make a mark. And then you are going to do the same for the remaining 34 pieces of data. Or should I say for the remaining 33 pieces of data. So you'll have 34 marks in total on this diagram, on diagram 11.8. All right. So we've plotted our points on, so that's part 1. So next we are going to, let's see, we're going to go on to part 2. So what type of plate boundary is represented in the diagram that we produce? So when you plot the points onto the diagram, you are going to see a very, very obvious trend. And that trend is so obvious that you'll be able to work out what type of plate boundary it is without any kind of trouble at all. So you'll be able to work out with relatively little effort, is it convergent, is it convergent, is it divergent, is it transform? You'll be able to crack that one pretty fast. Next, we're going to move on to part 3. So what is the range of earthquake depths in the vicinity of the Aleutian Trench? Well, all right, so here's the trench axis. So what's the depth of earthquakes essentially around the Aleutian Trench? So now this question is quite badly worded. Does it mean what's the range of earthquake depths across the entire diagram? Or does it mean what's the range of earthquake depths pretty much just where the Aleutian Trench is? Now, obviously, I'm going to be honest, you can go whichever way you want. You can say, okay, I believe what the question is actually asking is, what's the range of earthquake depths across the entire diagram? or do I believe what it's asking is the earthquake depths in just this area here around the Aleutian Trench? Okay, so give me the range for either of those options, but if you wouldn't mind, please label which one you're doing. Okay, whether you're doing the earthquakes for the entire diagram or whether you're doing the earthquakes exclusively around the trench itself. So please, do that just so I know. It just makes my life a little bit easier when I come to mark it. So question 4: why are the earthquakes more numerous north of the trench axis? Well, I can't really tell you that answer, but I'm hoping once you've produced the diagram on figure 11.8, you'll be able to crack that one yourself. On to question 5. What is the dip of the earthquake zone? Well, if you remember, a dip essentially is just an angle off the horizontal. So, once we've drawn our data points on, let's just say for argument's sake our data points are dipping like that. Okay, so obviously the dip is going to be, here's our imaginary horizontal line marked out by the ruler. Our dip is going to be what's the angle between our horizontal line and our dipping data points here. What's this angle going from here to here? And it's probably going to be about 45 degrees based on the angle of my pencil. And finally, for question 6, it asks you to label the North American and Pacific plates on the cross section. All right, now that's relatively easy to do. Next, it asks you to draw arrows to illustrate the relative motion of the Pacific and North American plates along the zone. Well, it just so happens that you have some lovely diagrams right here on page 168. Well, you look at that. They've labelled the Pacific plate and they've labelled essentially the North American plate right here, haven't they? So as long as you can work out what the orientation of your diagram is in figure 11.8, you've pretty much got that one answered straight away. And it's even being super duper nice because they've kindly added arrows showing you the direction of motion. Now I do wish to point out these arrows may not be referring to the direction of motion of the North American plate. Take a second and think about it. Don't just blindly look at what's on here and reproduce it on the diagram. You may make a mistake. Alright, and then that's it. And then the next page would be exercise 12. So that was it. That was exercise 11. I do hope that made sense. So hopefully you can get that done on your own. Of course, if you have trouble with it, please note that obviously I will be online for office hours at the stated time. All right, have a good day.